Thanks, Meg. So first, technical checks. Let me just make sure that you can see my first slide.
Yep.
Yes, fair. Yep.
All right, so I shared the red screen. Um, Thank you all for inviting me, and I'm going to tell a little bit about where we are with solar system processing, what is the current status, what have we been doing over the past half a year or so, and what are the plans going forward. So if you've seen my talk in Lyon last week, you will notice some similarities. This is, in essence, an expanded version of that talk, so some apologies in advance for maybe hearing again certain things you've heard last week. But think of that as a chance to ask questions in case any of that was not clear. So the solar system, I thought I would start first with a little bit of a bit more broader introduction into what is it that we're pursuing here, and why is it that we're pursuing this area of science, given the broader presentation we have across all science collaborations here. So the solar system itself is a fairly diverse place. I made a joke last week. I said when I started in this business, the solar system consisted of 4 or 5 types of objects that were all nicely, clearly delineated. You knew what a comet was. You knew what an asteroid was. Things are a lot more complicated today, as you can see by this diagram that I found on Wikipedia of all places. But it's quite useful. And it's good they're complicated because the science is complicated, and all of these overlaps and things we're discovering in the solar system are telling us a lot about the solar system structure, formation, and its evolution. So when we say, the reason why I bring this up here is when we say solar system science in LSST, most of what we're thinking about is the science that's going to be coming from small bodies of the solar system and dwarf planets. So there might be science related to the major planets. There will definitely be science related to satellites of planets, but that is not largely what I'm focusing on here. For the purpose of this presentation, anything moving in the solar system, but moving around the sun, so in heliocentric orbit, qualifies as a solar system object, and we will try to handle it appropriately. Other things that are moving will likely be detected as such, but we will not attempt to fit anything other than heliocentric orbits. So most of what we'll be looking at are asteroids and their larger cousins, the dwarf planets. So asteroids in the solar system are, here's a very nice montage of, I think at the point when this was made, all the asteroids that were visited by space probes. So roughly, to give you a scale, the 21 Lutetia that's shown on the left is about 130 by 100 kilometers. And so if you try to put a major city on Earth onto one of these, it would probably fit into a larger crater there. So they're rocks, mountains, whatever you want to call them, in the solar that are zipping through the solar system. Now that is one of the interesting aspects here. So most asteroids are between in the main belt main asteroid belt of the solar system between Mars and Jupiter. You see in this animation by Alex Parker of asteroids whose colors were measured by SDSS. You also see 2 swarms around Jupiter, and there are a number of other dwarf planets that are further out that are not on this animation here. The reason why I'm showing you this is one of the big things we'll want to understand with LSST is, first of all, make a census of asteroids, both in the main belt, near Earth asteroids, as well as objects in the Kuiper belt and beyond, and understand their orbits, understand their motions. The reason why we want to do that, there are a number of reasons, but let me give you a couple that are I think highly compelling to a broader audience. One is that where the asteroids are in the solar system, and even more so where the asteroids are not in the solar system, tells us something about the history, especially early history of the solar system. So I think this was brought to the forefront a couple of years ago, almost more than half a decade ago, with a class of models that began with the NICE model of solar system evolution that looked at the evolution of the solar system, starting with conditions that looked very differently from what we observe today in the solar system. So what you see here in these three panels, on the left-hand side is the potential initial condition of the solar system, where all the planets were fairly tightly packed, fairly close to the sun. So you'll notice that everything out, including Uranus and Neptune, are within 20 AU. And then you have a dynamical instability event that causes these planets to spread out, that causes the asteroids, and I should be more careful, dwarf planets that are out there to be disrupted from their orbits, many of them ejected. And what you have left out here is you have the solar system as we know it today, and the Kuiper belt and the asteroid belt as we see them today. And the way how this came about was as folks in NICE were trying to explain the observables, a number of the observables in the solar system, essentially orbits that are observed in the Kuiper belt, including events such as late heavy bombardment, and realized that this kind of a dynamical instability event early on in the history of the solar system explains it all. So this would not be possible without having a fairly complete census of the solar system and without having a lot of information about the orbital, the characteristics of the orbital distribution of everything from asteroids to minor planets to comets. A more recent example of how this kind of information that we're going to get from the census of the solar system is going to be tremendously useful are potential hints for an existence of another planet on the outskirts of the solar system. It's been occasionally called Planet X or Planet 9. The story here is that based on looking at orientation of certain ends on the what is it called? The perihelia of orbits of certain dwarf planets in the outside in the outer solar system, they seem to be in fairly non-random locations in orbital space. That points to something, to there being something that has placed them into those locations through gravitational interactions. And so that is the evidence that points to there potentially being a new planet. And when we say new planet, we're not thinking about something the scale of Pluto, but think about something more the scale of Earth or the ice giants. Looking for this planet or potentially finding it would be a major, I think, contribution to the understanding of the solar system, and one of the quite interesting potential things for LSST if it's not found or disproved before. So again, the reason why we can infer hints of existence of new and interesting things out there in the solar system is because we have cataloged a large number of orbits of small bodies in the solar system. This story goes beyond the solar system. So last year in October, this object was discovered, the first discovered interstellar object passing through the solar system. It's certainly not the first interstellar object passing through the solar system. It's just one that we've seen first. And this was an interesting discovery because the community essentially had only a couple of weeks to do all the observations that could be done on this object before it left, because it came in on a hyperbolic orbit and it spent very little time in the solar system. It was actually discovered on its way out. So with LSST, the hope is, depending on the model, to find anywhere between 1 and dozens or 100 of these objects. And either way, even in the first year of LSST, some interesting constraints are likely going to be put on these kinds of objects. Why are they interesting? Because if we can find them early, if we can observe them, they give us a hint of what they've gone through in their in the planetary system they originated from, which makes them highly interesting. And now going back closer to Earth, this was one of the big motivating factors early on for LSST. It's the NEOs and Planetary Defense. So what I'm showing you here is a video from an event above a place called Chelyabinsk in Russia that happened on February 15th, 2013. In this case, a fairly small meteor entered the atmosphere about Chelyabinsk, roughly about 20 meters or so, and caused quite a lot of damage. The light from the meteor was the usual story, brighter from the sun, brighter than the sun, visible more than 100 kilometers away. But the interesting thing to me was that it exploded in the atmosphere, but the damage that it caused on the ground made about more than 1,000 people seek assistance in emergency rooms, typically due to broken glass and things of that sort. If a larger object did this over a more populated area, over a major city, you can imagine that that would be a fairly bad day for everyone. And one of the things that the asteroid community has been working on over the last couple of decades is to try to find and identify these kinds of objects. And LSST is going to bring a major new resource for these types of studies. Okay, final thing in this little tour of asteroid science and opportunities is something new, something that may look, to be honest, a little bit on the science fiction side, but less so with every day. And the idea here is to actually go and mine resources from these asteroids. So what I'm showing you here is a slide produced by actually a local company here in Seattle area, Planetary Resources, who are planning to try to go to one of the nearby asteroids and understand how its resources can be mined, either for further exploration of the solar system or to bring them back to Earth. So you have everything from getting water for solar system missions to bringing back precious metals. And these kinds of things are actually becoming feasible with advancements in rocketry that we've been witnessing over the past couple of years. So discovering small asteroids near Earth might give us opportunities that go beyond science and beyond planetary defense that honestly we haven't been thinking about up until a few years ago. So what will LSST discover, or what is LSST expected to discover? In all these classes of objects, LSST is going to make contribution, some more than the other, but even the smallest, quote-unquote, smallest contribution that we're going to make in main belt asteroid is going to increase the number of known asteroids by almost an order of magnitude. So this currently known number is slightly out of date now. There are about 700,000 known main belt asteroids. And depending on what we assume for the model, we're going to, with LSST, we're going to see anywhere between 5.5 million and going all the way up to 10. Jupiter Trojans, it will increase the numbers dramatically, and transit-tuning, and it's going to be a fantastic machine for discovery of transit-tuning objects. So these are the capabilities of the LSST. What I'm going to be talking about in the rest of the talk is how do we make data products like we do with everything else in LSST? How do we make data products that enable scientists downstream of the LSST project to actually take these asteroids and either and turn that raw information on here's an asteroid in the solar system into science. So LSST will produce, the way I like to think about it is when it comes to the solar system, the LSST will provide three types of data products that enable solar system science. One or two of them fall into the class of prompt products, what we used to call level 1, and then the third are the data release products. So I'm going to go through through these three types and tell a little bit about each one of them, and then I'll go into a little bit more detail about the changes we're planning to make to how we build the daily orbit catalog, which I think is going to be the most interesting thing here to the solar system folks in the collaborations. Um, so I've usually when I would give this or talk somewhat to this earlier, I would just say there are two types of data products. There's the orbit catalog, and there are things that we're going to be doing in data release processing. But I feel that actually hides certain things that we're going to be doing at an even more real-time scales, and that is the ability to quickly identify and follow up fast-moving objects by looking at trails, trail objects or streaks. So that's why I've now started separating this and talking about three types of data products, just to bring your attention to the fact that, as you know, there will be a real-time data stream of alerts coming from LSST within 60 seconds of each observation. And in that data stream, we'll have the usual measurements of centroid astrometry, PSF photometry, aperture photometry, and so on. But we will also have measurement in that real-time stream of what we call the trailed source models. So to each observation, we will fit a model of an object that's moving, and we will fit for the best fit direction of motion and the magnitude of motion. So in effect, we will tell you if this object is moving, how fast it's moving, and what direction. So by comparing for example, the quality of the fit in this trail source model with the quality of the fit in the point source model, or with what the aperture photometry is telling you, it will be fairly straightforward to identify trail sources like the one I'm showing here on the image, like the example I'm showing here on the image on the right, and react to them immediately. So I think this is one of the potential things that is still fairly unexplored on the LSST side, and ZTF, which is trying to test some of these ideas that we had for LSST, is doing something like this and has actually put it to really good use, and is finding NEOs quite successfully by looking at these trailed objects almost in real time. So this will be coming out within 60 seconds of observation. On a daily cadence, based on what we currently have in the baseline, now I'll talk about the changes in just a second, we will be producing an orbit catalog we'll be detecting objects that are not easy to identify as asteroids just based on a single observation, because they don't trail, they truly look like stars. And we will link those objects together into orbits, and then produce that catalog of orbits and their physical properties essentially on a daily basis. So based on the current baseline, and again, the caveat is that I'll tell you something about the changes in just a few minutes, but here's what the current documentation is telling us. Every night, at the end of every night, we will take all the objects that were discovered in that night and over the previous couple of weeks, I should say, we will take all the detections that we cannot associate to static objects over that night and over the previous couple of weeks. We'll take those detections, we will find those that are consistent with being a moving object on a heliocentric orbit. We will associate those into associations of objects into associations of observations that correspond to what we call solar system object. We'll compute an orbit for that solar system object, and we'll compute some physical properties of that object based on the photometry we will be getting from LSST. So things like absolute magnitudes, and later on, when there's enough information, enough auxiliary information, perhaps things like slope parameters. The reason why we are building this catalog, I think, are important to understand. One of the primary reasons is that we want to have an up-to-date catalog on an essentially nightly basis, as opposed to every month or every year, because we want to enable follow-up of these objects. If an interesting object is discovered, we want to know about it early on, so as to enable follow-up. The second reason is that what we want to do is enable association of objects as soon as they're discovered, so that they're not mistaken for example, interesting transients. So both of these desiderata, or both of these reasons, make us want to have this catalog be as complete as possible. And this is one of the motivations for the changes that I'm going to be talking about in just a second. So this happens on a daily timescale. Every day, new objects are discovered. What happens on a yearly timescale is, in essence, we repeat what we do every day, but with data that's of higher quality. So data that's of higher quality and a fairly well-controlled versions of the software. So I should have mentioned in the prompt products, in the daily orbit catalog computation, because we are going to be biasing towards being as complete as possible, if we discover bugs in, let's say, MOPS or any of the software downstream that makes us incomplete, or that makes the catalog, say, overwhelmed with incorrect linkages or things like that, we will fix it as soon as possible. And that is true throughout the level 1 system. That is kind of the posture we've taken. Level 1 is to enable rapid follow-up. Therefore, if something is identified as an issue, a software fix will be made to fix it as soon as possible. Now, that means that over the course of the year, you may have a number of software changes that are going to affect things like selection functions of the survey. And that will all make it fairly difficult to understand what the selection functions are and to do any kinds of statistical studies with these types of catalogs. So that is the primary motivation for data release products. In data release products, the goal is to provide a catalog of moving objects that truly enables estimates of completeness in population studies, where the selection function is well quantified, well understood, that's generated with a single version of MOPS, that takes advantage of improved photometry and astrometry that's available in data release processing. And this catalog will also include LSST only information. So what that means is, I'll tell you in a second how we're planning to change the nightly catalog. In essence, the nightly catalog will become the catalog that the Minor Planet Center is producing, and that catalog is not just built using the information from LSST, but also from other surveys. As you can imagine, that makes it difficult to understand what the selection function of that entire catalog is. So again, in data release processing, we will deliver a catalog with well-controlled versions of software, well-understood measurements of both photometry and astrometry, and using only LSST information to enable these kinds of population studies. But otherwise, the essence of this processing that happens in data release is going to be nearly identical to what we would have done on a nightly basis. Let me talk a little bit about the solar system processing flow that happens every night. So this here is a fairly and high-level coarse-grained schematic of what will be going on in a night-day cycle. If we start with the night side, let's begin with observing. So LSST will be observing during the night, and the evening before, we will generate a certain, you can think of them as help files or as cache files, to allow us to rapidly associate any known objects to rapidly associate any moving objects that are already known to catalogs that LSST has. So after the observing is done, any objects that are not identified with static objects or already identified with moving objects will be passed on. Any detections that are not identified with static objects or already known moving objects will be passed on to MOPS. MOPS is the moving object processing system. It's a piece of software that then takes those detections and attempts to link them into candidates for moving objects in the solar system. Those linkages, so MOPS will take those linkages at the end of the night, or take those observations at the end of the night, attempt to do linkages, and then do two things. Like, this is according to the current baseline. One thing that's going to do is he will report any new linkages to the minor planet center, the way that is customary and done today by all surveys, all asteroid surveys. And the second thing it's going to do is to use those candidates or to add those candidates to a catalog that LSST would preserve and maintain internally of moving objects. So those linked object candidates are added to the catalog. Then the catalog itself that will start accumulating more and more linked objects and orbits will undergo what we call a recomputation step, where we look at all the newly discovered orbits. We'll look at the orbits that we already have in the catalog and try to understand which ones might go together, in the sense that you may have had an object that you observed 3 years ago that corresponds to an object that was rediscovered yesterday, but not initially understood as such, as a rediscovery, but mistaken for a new object. So there's a lot of bookkeeping that goes into that. That is that's what this circular arrow is meant to convey. But at the end of that process, new objects are incorporated into the orbit into the orbit catalog that LSST maintains. The orbit catalog is made public. The orbit catalog goes into the ephemeris precomputation stage. Here we precompute which objects we believe we're going to see the next night, and then those are used to associate objects in the night. So this is roughly the nightly loop. You have observing, you have MOPS trying to find new objects, you have those new objects added to the orbit catalog, with the catalog recomputed to keep it as correct as possible, and then using that catalog, we try to associate new objects. We try to associate already known objects next night we observe, and this goes on every day, or every day and night. There's a number of issues with this scheme that, as we started implementing it, we started understanding it more and more. One issue is that the arrow going to the minor planet center in here is one way. So in essence, we report to the minor planet center, but we do not ingest back or not explicitly ingest back the data from the minor planet center about, for example, designations that minor planet center assigns, and so on. So we have found ways to work around that, to associate both objects. Every single object that's discovered, we could associate it with the internal LSST orbit catalog and the minor planet center designation. But the more we thought about it, the more it turned into a bookkeeping headache, and not just for us, but for scientists downstream who are meant to use this catalog. In essence, you would have to understand, or there would be 4 options for example, in each alert on whether an asteroid would be associated with an LSST catalog, with the minor planet center catalog, with both, with neither. Then there will be interesting potential problems if a minor planet center links asteroids one way, LSST internally links asteroids another way, and many corner cases that would need to be resolved that would simply cause headaches downstream. Another problem here was that we didn't plan to cross-reference the LSST catalog to the minor planet center catalog, so this was left to the community. So everybody would have to write essentially the same code to establish that some ID in the LSST catalog is really an asteroid from the minor planet center catalog, and those kinds of codes are usually fairly easy, except when they're not. In corner cases, again, there are going to be problems. And the biggest problem here, at least in my view, is that tracklets, we have MOPS that links tracklets into potential asteroids, and tracklets that are never linked would never get reported essentially anywhere, definitely not to the minor planet center. So the objects where LSST's tracklet could be linked to, for example, a tracklet from another survey, become lost. And that is something that we haven't quantitatively evaluated how much of a difference this would make, but it may be on order of a couple of percent, and certainly worth pursuing. So we looked at whether we could do better and started discussions about this almost a year ago, both with the Minor Planet Center and with the folks in this Solar System Science collaboration, and came up with this scheme instead. So if you look at the previous plot that I showed you, or the previous diagram that I showed you, the difference is that now instead of the 2 boxes on the day side, we have 3. And one of those boxes is recompute MPC orb, and it's called differently because it would happen at the Minor Planet Center. So the idea now is to do observing, to collect observations, to take all the observations that are not associated to static objects, to pass them on to MOPS on the LSST side, have MOPS discover candidate linkages, but then instead of us computing the final orbit for those linkages, we would submit those linkages to the Minor Planet Center. The same way that all surveys presently that are operating at present, especially the asteroid surveys, the NEO surveys do. So we would pass that to the Minor Planet Center. Minor Planet Center would take that, would recompute their orbit catalog, their internal orbit catalog, within a day. They will republish that orbit catalog, incorporate LSST observation, incorporate all the other observations that may be happening at the same time, so any other project that may be going at the same time, generate a new Minor Planet Center MPC orbit catalog, put it out there. We would ingest it into LSST. We would get our orbit information from that catalog. We would compute on top of the orbit information. We would compute all the physical characteristics that come from LSST photometry, in essence. So things like absolute magnitudes and such. And then we would use that as the catalog for ephemeris pre-computation to support observing the next night. So if you're thinking about what does that change in for the Solar System data products, it makes a change in the sense that the LSST orbit catalog that we had before, the SS object table in the DPDD, you can think of that now as being split into 2. The orbital information that was present in the SS object table and that we thought we would, or we were planning to compute, would now come from the MPC orb catalog. So they would be computing that for us, and that orbital information would include, again, not just LSST, but all the information that's at that time available to the MPC. And then the other half of that table, the various physical quantities, would still be computed. It's just that the source of the linkages is now coming from, or I should say the orbital information is coming from the MPC, and we use that information to determine which LSST observation belongs to a given asteroid and compute the physical properties for the asteroid. So that is really the change. On the data release product side, not much changes. I think in essence nothing changes, because on data release product side, we still will compute an LSST only orbit database and compute the physical quantities the same way that we did before. So why do we do this? We think that this brings significant improvements. So first of all, the orbit catalog that's used for association in any given night is now maximally complete at all times. We had this day 0 problem in that if we observed Ceres, the largest asteroid there is out there on day 0 of LSST observations, we would think it's a new asteroid. The attempts to fix that, or one could fix that by saying we're going to associate both against the LSST internal catalog and the Minor Planet Center catalog. But as I mentioned, that brings all kinds of bookkeeping problems that this neatly avoids. So for everyone not in the Solar System Science collaboration, I think this is excellent news, because this means that we will be much more successful at removing contaminants for all other kinds of science, for example, supernova, fast transits, and so on, because this catalog is going to be significantly more complete. It solves the cross-matching problem. There now isn't anything to cross-match. There's no need to cross-match two orbit catalogs. It reduces, I think, community confusion. There will not be an LSST catalog and an NPC catalog. There will be just a catalog of objects in the solar system. And I think it's nicely consistent with what's happening these days, and where I think something that will make I think everybody's life easier. This one is, I think, fairly interesting because people are always wonder, how do I actually work with LSST data, and how do I access it? What's the LSST science platform going to look like, etc. Well, it turns out that with this change, whether one will need to significantly change their tooling to work with LSST data, because, for example, of different formats. And with this change, we become standardized. There is nothing special to take advantage of, nothing special to be done to take advantage of LSST data, especially if all one cares are about the orbits. It's essentially all in the Minor Planet Center's orbit catalog. If you have tooling that works with the MPC, it will just work. It will just continue to work, except that that catalog will start growing significantly when LSST data starts coming in. And I think it makes our data much more accessible and useful, even beyond the black belts that have been thinking about this for a while now. It also places LSST into a more general framework of how surveys operate today. Especially, virtually all the observations are sent to the Minor Planet Center for incorporation into their databases. We now become a part of that framework rather than a separate thing on the side. It's worth to understand a little bit of history there. That the reason why LSST built or planned to build so much internal infrastructure that replicates in many ways what the Minor Planet Center already does was because at the time LSST was conceived, the volumes of data that were being talked about were something that was just impossible to handle at the Minor Planet Center. In the meantime, LSST is coming almost a decade later than when it was originally envisioned and when these plans were drawn up. Moore's Law works to our advantage. The Minor Planet Center has actually expanded significantly over the same time period. And other surveys have shown that they are actually capable of intaking a significant amount of data. So a lot of the work that they did to prepare for pan-stars will translate over to LSST. And so we can just plug into a lot of that framework. Interestingly, it also opens up the possibility for us to submit all tracklets to the NPC, including trails. So they're very interested to relax their requirement for tracklets to essentially be 100% real. Most of our tracklets are going to be probabilistic. They'll have some probability of actually being real or being misassociations. And we're driving some of that evolution at the MPC that will allow them to intake, in essence, everything that we have. And that allows not just the Minor Planet Center, but the entire asteroid community to begin looking at things like cross-survey linking. So imagine the first discovery being made, the first tracklet, the first two pairs of observations being made by LSST, the second two pairs being made perhaps by pan-stars, and the last two pairs being made by, I'll just make something up, let's say W first, just to be exotic. Right now, those kinds of discoveries would not be a discovery because they're in separate databases. If you send everything, if you have everything in the same database and allow everyone to try to establish those kind of linkages, that will allow a much significantly more complete discovery process. Now, the second set of advantages that we have here is that we also, by doing this, we also evolve together with the MPC and drive some of their evolution. So one of the things that we'll be driving is that there are going to be, we're going to be devising a new orbit format for this orbit catalog that includes covariances, that a format that is much more applicable and say applicable. much easier to use also for things like Kuiper belt objects with short arcs. We need this internally to compute reasonable error ellipses, really for association. But this is going to have, I think, a much more broader impact community-wide because this is the kind of information that's being asked for a while now. We'll be pushing for some updates to the ADAS data exchange format. Updates such as the ability to support probabilistic tracklet associations. So in essence, to assign a probability to each tracklet, to make it possible to have each observation be assigned associated to in many tracklets. We'll be updating that format. I apologize, I have a bug there. It's not update to the catalog format, update to the ADAS XML format. And we're also driving some of the improvements to the MPC services. So they'll be coming out with an improved and downloadable NP checker, in essence, a piece of code that allows you to quickly compute which asteroids are in your field of view. And we have some ideas on how to do standardized pre-compute, or how to develop standardized pre-compute position formats. So once this is pre-computed, any survey can essentially use the same tool and download these pre-computed files in the same format. So bottom line, I think here is that we'll benefit from this work that the NPC does for the broader community, but also it'll go vice versa as well. So the broader community will benefit from the work that we do in our understanding of what's needed to support these kinds of scales of observations and numbers of asteroids that we're going to discover. Okay. So this is ongoing, and we have just started to put this into documents that we're going to start circulating over the summer in the collaboration. So we expect a lot of feedback there. I presented an early version of this in Utah at the DPS meeting. Incorporated a lot of that feedback back. It was generally positive. We'll continue doing that. We want to make sure that we come up with something that we can both do, given the resources that we have on the LSST side, and it's going to be useful to the community. So I have a couple of slides with updates on where we are with MOPS, and then I'll open it up for questions. So MOPS is the part that the software pipeline that takes the newly collected observations and tries to link them, tries to put them together, associate individual source detections to a single moving object that's going through the solar system. You've probably seen this slide a number of times already, how what the current strategy is to discover new asteroids. In essence, we do 2 observations every night with the hope that will generate a tracklet. So 2 nearby observations of the same asteroid that can be associated relatively unambiguously. So when you accumulate at least 3 nights worth of tracklets, you can try to, in essence, draw a line through them, extrapolate from the first one to the next one, and then from those 2 to the next one, and so on, up until the point where you're confident enough that you have a potential association that you go ahead and do initial orbit termination and differential orbit termination and send it to the Minor Planet Center. The issue with this algorithm has always been that if you are overwhelmed by false positives and an image differencing, that's a possibility. Pan-STARRS famously had issues with that because of the hardware issues on the camera. You might be overwhelmed by the numbers of tracklets, by the potential, by the combinatorics of the problem, the need to try to link every possible, to try to check every possible linkage, and that leads to a fairly inconvenient scaling for something like ON cubed for the number of tracklets. So we spent a lot of time over the past couple of years trying to assess how well LSST is going to do in this area. And I'm glad to say that this paper that Lynn Jones has been leading has now been published. It's in Icarus. The bottom line is that our conclusion is that MOPS will satisfy LSST moving object linking requirements. There was a nearly simultaneous paper by Steve Chesley and Peter Verish, then at JPL, now Peter's at MPC, who've done the same kind of study. We're using the same algorithm, but a different implementation and reach the same conclusion. So we're now fairly confident that this will just work, and we're moving on to implementation. Just a quick snapshot for those who are interested in LSST as an NEO discovery machine. NEO stands for Near Earth Objects. How well will LSST do with NEOs? The baseline survey already will find about 73% of all known NEOs. Again, this is a fairly model-dependent statement, but using models that are presently available, 81% of PAJs. And then we also looked in this paper what would happen if we changed the survey, extended it to 12 years with some changes, and how would that change the discovery rates. We're able to show that PAJ discovery rate would go up by something like 5 percentage points. The way to think about these numbers actually is not that it goes up by 5 percentage points, but you should subtract 100 minus this number. So what this means is that 20% of the population will be unknown, and what this means is that 40% of the population would remain unknown. 14%. So that means that this change would discover a quarter asteroids that were quarter PAJs that would otherwise remain undiscovered. So if you really are in planetary defense mode and trying to discover all of them, it's actually not insignificant. It's quite a significant number. The MOPS algorithm that I mentioned, I think we're fairly confident that it's going to work, but that hasn't stopped the community to think about improvements. We've been thinking about them as well. There's been a paper recently by Matt Holman, Matt Payne, and colleagues from the CFA, from NPC, presenting a new way to do linkages. So in essence, what they point out is if one transforms the origin of observation to the sun instead of the Earth, the apparent track of an asteroid on the sky or in these projections stops being fairly nonlinear, as you can see it here, and turns into something that's more like a line. And then based on the fact that you have the tracklet, therefore you have an estimate of the motion, you can project all those tracklets into some reference time, turn them into clusters, and fairly easily discover asteroids and turn your asteroid linkage problem into a cluster finding problem. And this changes the scaling from O(n) cubed to O(n) log n, as this paper presents. So that would be significant improvement over what we have now, and this is something that we're definitely looking into. It's fairly likely that we're going to adopt this algorithm. We've been talking to Matt about this for a while now, but I think we still need to demonstrate and evaluate its performance in LSST-like conditions. Their paper was fairly didn't really go into much detail on how false positives might affect these scalings and so on. So we're quite optimistic that the major advances can be made in linking beyond MOPS. So this brings me to my last few slides, just to give you an idea of what are we doing going forward and what have we done recently. So one of the big things that we're doing is we're increasing or enlarging our team. So at the moment, the solar system, LSST solar system DN team consists of Joachim Moens, who's a graduate student here at the University of Washington, and at present he's about 40% on working on MOPS. I am about 25%. I will be, in the long run, I'll be working on this 25% of my time. Over the summer, it's actually be bumped up to something closer than full-time, in order of 75-80%, just to get things started. And the key person here, I think, is a senior postdoc who we've already identified a very good candidate for hire, who we hope to bring in fairly soon, and who will work on this full-time. So it's a fairly small team, but we're definitely trying to be creative in how we deliver things and deliver everything that we're hoping to deliver for the community. We also get support, of course, from the broader DM team, and one person I would especially mention here is Lynn Jones, who's the LSST performance scientist, who's been donating a lot of her free time to just get this running, to get us further along in all the LSST, in all the solar system work than we otherwise would. So over the past 6 months, over the past period, there has maybe I should start from the back of this slide or from the bottom of this slide. Due to various scheduling constraints, we've had we essentially paused a lot of the work on the solar system. So we had only, I looked at it today, roughly 0.1 FTE working on the solar system over the past 6 months on average. But we did manage to steal some cycles from other efforts and keep things moving along. So we had a major meeting with the MPC in December. We have an internal memo with about 24 actions that came out of that. We'll publish a technical note later this month with the summary of those actions. We have been working with JPL on initial orbit determination. We've incorporated the code that Davide Fernocha wrote for us, a Python implementation of IOD. I had a week-long visit by Siegfried Egel, one of the JPL researchers, to integrate this just this past month. And I think the key thing here is we asked and were approved to add one more person to the MOPS or to the solar system team. So as I mentioned, we have an excellent candidate. We're looking to see if they can start as early as September, and that will increase by a factor of few really the resources we have working on LSST on LSST asteroids. So going forward, bringing on additional person is priority number one right now. We're working to document the details of NPC plans, so we have something that we can share with the collaboration that is in some coherent form that can take where we can take comments and then propose formal baseline updates and changes. We'll continue developing MOPS, looking at this new algorithm, and one of the things we'd really like to do is to deploy and test in ZTF. So there are two aspects to that. One is the real-time alert component, so looking at streaks, and the other is running MOPS on ZTF public survey data, whose cadence, I'm not sure if that's broadly known, is actually designed to mimic LSSTs. So if you want to prepare for LSST today, you should really be looking at what the ZTF is delivering. And just to drive that home, I showed this slide in Lyon last week as well. ZTF has just started publishing the alerts they discover every night. We were hoping to make it actually available in the form of a stream, but we have the stream ready, but the public brokers are not quite there yet. We're working with them to be ready to serve the community sometime later this summer and in the fall. In the meantime, what we've done is we have started putting all those alerts onto a website where they can be downloaded from. So if you want to see what the technology is going to look like that LSST is going to be using, the formats, the kinds of tools you're going to have to be working with to access the stream in real time, this really is a fantastic data set and a fantastic survey to be looking at. And again, we're planning to use it to test a lot of these things a lot of these things we're developing for LSST ahead of time, even before LSST is on the sky. So with that, I will stop. Just mention that next month is the first Solar System Science Collaboration Readiness Sprint, and we're looking forward to that to discuss a lot of these things in a lot more detail. And we're very happy to essentially be back to working on solar system processing after about a 6 month hiatus, expanding this team going forward. So let me stop there and take some questions.
I guess I'll just start going down the list. So for Michael, can you say something more about what specialized observing modes, especially deep drilling fields, can do for discovering KBOs or TNOs?
I think you may actually be a better person to answer that.
Depends on what. So we can do with a lot of things. Typically, we do want that second observation at night because it removes our contamination for asteroids. I would say for me personally, and it's my next question, I care about things that are beyond 200 AU, which MOPS will not find because it won't move between an image. So at least current thinking has been that you need to have that second image on one night to be able to move those things, or in other ways be able to take out those faster moving objects. So for me, some of the cadence is making sure we've got that second image, unless we can really show that that's not needed. Where I've always had at least on one night 2 images, or many, many, many images, spending a week to be able to do that. So I think for outer solar system, we'll get size distribution from the deep drilling fields, but we're not going to get as much about finding them at distant orbits from the deep drilling fields. We'll get that from other things like the wide survey and getting the northern ecliptic spur. So getting more objects is everyone's number one science case. They'd be willing to give up light curves and other things to get the northern ecliptic. So I guess that's the other thing that's kind of come out of the community. I don't know if you want to comment any more on that, Mario, or have anything else to say on that.
That's a good summary.
I guess my question is that it was not clear from Eric's talk on the alert stream that, again, you will find things that MOPS doesn't link. Like, again, if I want to find Planet 9, it's sitting around beyond 200 AU. MOPS will likely not find it because we won't see motion in one night. How would I search that? It sounded like the alert stream sources may not necessarily be searchable on the LSST sort of DAC, and I'm not sure if that's true or not.
That's not, I think that must have been a misunderstanding. All the sources are going to be in a database, in a quite searchable database. And perhaps where the misunderstanding is coming from is that there's also going to be a log of all the alerts, like literally the bytes that were sent across the wires as more of as an archival thing. Those will not be searchable, but for those you will need to know the ID of the alert. But all the information that's in those packets will be in a searchable database. So. Yeah.
And the DIA object or source database, whatever this is from the alert stream, that will be available nightly, or is that, I think that was the question.
That's available in real time, in essence.
Okay, okay, because it sounded like that.
Yeah.
Yeah, okay. It
Sorry,
sounded like it was only from, the way it said it was that like it wasn't clear that, I guess, the data from alerts would be searchable the next day. It should be.
Unless something has changed, I'm sorry, I should actually refer to Eric on this, but I think
he referred to you, so you might have the right answer.
The DPDD is I think quite clear at this moment that we promised to make that available within 24 hours, and I think that the technical implementation is in essence that it's available immediately.
Okay, thanks. Sounds like Michael wants me to ignore his second question.
Yes.
So mine, and you probably already know this, is that this is the first time that I think David and I and the community is hearing exactly what you and the MPC have planned. And when everyone brings up MPC, the orb file, I get twitches because I actually don't think it's that very good. It doesn't have uncertainties and it doesn't have a lot of things that we use that, especially in outer solar system. We actually fit our own orbits, and I've never actually used the MPC other than for if I'm doing something with a sample of I want all known objects, or I want to check that I have one of my objects might be already known. So you rely on it to fit an orbit. So it's a little scary to feel that if I look at the current MPC orb file, it has none of those things that are in that sort of data-based schema structure that's been proposed for LSST previously. And so that really scares me. And so I'm just wondering, how is that being changed? What's the timeline for telling us?
So I think that,
and when is this all going to be finalized and really available?
So we presented kind of a draft of this back in October, and then we had the meeting with MPC in December, in essence, to figure that out, like to what degree can they change things internally, like the orbit formats specifically. And Matt Holman was quite happy to go ahead and do that, and being Matt, he immediately started devising what is the optimal way to encode uncertainties for Kuiper belt objects and so on. So that's a process that I think it will take a on order of a year or so, and we need to manage it. We need to make sure that there's a loop between MPC and the project and the collaboration to make this into something that's as useful, as broadly useful as possible, so that you folks perhaps don't need to continue fitting your orbits. But I would think about it. This is a case where you're choosing, I would say, the best possible alternatives from a number of potentially unsatisfactory choices. The alternative would be that LSST tries to do something on our own with, in essence, no resources, right? Because the idea is that the LSST will not be actively housing a sizable solar system team to understand the optimal formats and so on in operations. It's going to be a fairly automated operation to make these data available and then for the community to take it up. What we're trying to do here is to make this data available in a way that benefits as much as the community as possible, and to push the community aspects, so let's say the MPC, to actually deliver beyond what they're delivering today and give you orbit catalogs that are that might be even directly useful for what you're trying to do. Because if you look at what we were going to deliver, it's actually a copy of what's it called, of Astorb plus error covariances, right? It's not that different from what comes out in MPC orb already. So we're actually trying to make this better.
Yes, but I guess the thing is that we're not. I guess my worry is that you and the MPC and project are talking, but we're not having, I guess, a closed loop with having the community involved in it. And so I can think of things for solar system. You might be thinking more about asteroids, and how do we make sure we're all talking about it? Because I guess my worry is that, and the worry has been, is that the MPC has to scale up to a significant level, and they've started, and are they going to get there on time, and what happens if they don't? And so if they can't deliver orbits in 24 hours or in reasonable amount of time, what is going to happen and on day one? And so I think it's I think having a more of these presentations to the SSC so that we can have these discussions, because I guess that's all my questions of. There are action items, but even from the MPC, we're not hearing anything. And I know they're part of the community, but they're one aspect, right? So JPL Horizons is another, and are they going to be involved as much? And I get why you might select the MPC, but I think it's just a little bit of a surprise to hear that only in the yearly catalog will there be an orbit fit. Or it sounds like there will be an orbit fit in the yearly catalog, the annual release.
Yeah, that's right. I mean, I would say, we'll it's definitely, in kind of work time, this has all happened last month. So there seems like there's a delay there, but it's a loop that we're trying to make as tight as possible, given the resources we have. And the issue here, I think, is to think about. Let's try to find a way to make what MPC is going to be doing for the community as useful to as broad range of the community as possible. I know that especially the asteroid folks are extremely excited about this. If there's something that's problematic on the KBO side because of this change, we'll try to find a way to fix that as much as we can.
Right. I think I would suggest to project to really consider that if you're going to have these meetings, really think about having some representatives from the SSC in there as well, or afterwards giving us a summary, because I guess right now my concern is that we got a little bit in October, and then this is the first time I've actually heard anything other than sort of watching your talk last week.
Yeah.
So I think that's just something
again,
that, and generally I think is a concern.
Yeah. I think the issue here is that we've had this pause of work over the past 6 months. So it feels like it's been a long time with no communication, but in effect, in terms of work that has been done, this is effectively January for us, right? So it's the month after the meeting, and now we're putting out all those papers and so on. And I think that's something that I hope the collaboration can understand as well. On a project of this scale, sometimes we have to pause in certain areas and then continue later. But one of the things that we really didn't do well is communicate that, and we'll try to work on that better going forward.
Yeah, I think at least in looking at them, most of them are my questions, I think, at this point. is, getting a timeline of all of this and it all written out. And I guess my worry is that, and I think the same thing for both MOPS and everything else with data, all the data pipelines is, when do these actually come online? And I think that's part of this, that I get the pauses and everything, but as we add new things or waiting for other people to then, or other community institutions to provide things, that we also need to prepare for that. And we've been working in the last 6 months. And so I think if project in general can decide about how best to communicate these changes to the data structures and timelines, that would be really helpful. So I'll leave it at that, but I just think that this is the first time the SST is actually hearing any of this. And so hopefully we can brainstorm about how to communicate that.
Because it was actually presented in October, but fine.
A little bit, but it wasn't finalized. So I don't think it was clear to me, and David might disagree, of exactly how that was going to be worked out. So yes, you did discuss it, but it sounded like it was very preliminary, where this sounds much more sort of thought out and final. So I think just in terms of moving forward, if we can figure out ways of communicate, it sounds like Solar System has a lot of development to do in terms of pipeline and data formats, of just, if there are timelines and dates, that helps us prepare and start writing software to know what the new MPC format will be and things like that, and whether or not the MPC is willing to give us allow the community to give input. So I don't see any other specific questions. There was one that was just asked if will the MPC be supported throughout all of LSST? So it is, I answered that, but I guess you might have a better answer for, since they are a separate institution, are they going to commit to being funded and providing this for the 10 years?
They have been designated by NASA as a major, I think the term is node, to support their asteroid or solar system exploration mission. They have a 5-year contract that is, we have no reason to believe it's not going to be extended. So I think the risk there is fairly low. At least that's after studying what they've told us. I think that's kind of my assessment of it. And just historically, they've been around for already a couple of decades, much longer than LSST itself.
Are there any other questions? I think there's one more. If the data release orbit catalog does not include info from the MPC, will there be distinction between LSST and MPC catalogs? I guess in terms of, it sounds like in terms of the data release, but
yes,
I just want to understand.
Right. Sorry, say again.
Yeah, so the context of this is that you made the strong point that the MPC and LSST catalogs will be identical, but that will not be true for the data releases.
Correct.
Am I saying that right?
Correct. The data release catalog is a completely separate. It's completely separate from LSST, from MPC, and in fact, it will cause some curious artifacts in that catalog. In that we probably won't have the brightest asteroids in it.
Right.
they will saturate.
Right. Yeah. Thank you.
Any other questions? All right, well, let's thank Mario. Thanks very much for the update.
Right. Thank you. And I'll put these slides somewhere on DocuShare and let you know where they are. And happy to take questions and feedback on this. I think this is extremely useful to us as we're trying to put this together into a product that we can deliver.
Mario, you can send slides to me because they are supposed to be linked together with the recording at the scientists page on lsst.org.
All right, will do.
Thank you, Mario.
Thanks, everyone.
Okay, bye-bye.